Most nations view energy through the lens of import and export. For India, energy is a question of absolute sovereign survival. While India holds less than 2% of the world's uranium, it sits atop nearly 25% of the global supply of thorium. In the 1950s, Dr. Homi J. Bhabha realized that traditional nuclear paths would leave India perpetually dependent on foreign fuel. His solution? A three-stage master plan, designed to turn a resource vulnerability into a permanent strategic advantage. This is the story of the closed fuel cycle, a system where one stage's waste becomes the next stage's weapon of energy independence. To understand the sheer scale of this three-stage program, you have to understand the geopolitical isolation that forced it into existence. In 1974, India conducted its first nuclear test, codenamed Smiling Buddha. The global backlash was immediate and severe. The major world powers created the Nuclear Suppliers Group, or the NSG, almost entirely as a response to India. An era of atomic apartheid began. For over 3 decades, India was cut off from the global nuclear trade. It could not buy uranium, it could not buy reactor components, and it was denied advanced technological assistance. While other nations bought off-the-shelf reactors from the US or Russia, India had no choice but to look inward. The three-stage program was no longer just a scientific theory. It became the only lifeline for India's nuclear survival. The scientists at the Bhabha Atomic Research Center had to build the entire supply chain from scratch. This isolation heavily influenced Stage 1, the pressurized heavy water reactor. Conventional reactors require enriched uranium, a process that was strictly blocked by global embargoes. India's pressurized heavy water reactor, however, used natural, unenriched uranium mined domestically. By using heavy water as both a moderator and a coolant, India bypassed the need for forbidden enrichment technology. But the real genius of Stage 1 isn't the electricity it generates, it's the byproduct it leaves behind. As natural uranium burns, it creates plutonium-239. This plutonium is the crucial chemical key required to unlock the second and far more complex stage of the cycle. By the mid-2000s, India faced a crisis. Its domestic uranium reserves were running dangerously low, threatening to throttle the entire three-stage program. Then came a masterstroke of Indian diplomacy, the 2008 Indo-US Civil Nuclear Agreement. India managed to secure a unique waiver from the NSG, allowing it to buy foreign uranium without signing the Non-Proliferation Treaty, NPT. This was a geopolitical checkmate. By importing foreign uranium to fuel its civilian Stage 1 reactors, India could suddenly free up its scarce domestic uranium, strictly for its strategic military reserves and its experimental breeder programs. The 2008 deal essentially bought India the time and the fuel it needed to crack the physics of Stage 2. Stage 2 is where the physics becomes incredibly difficult, and where India recently made global history. On April 6, 2026, the 500-megawatt prototype fast breeder reactor, PFBR, at Kalpakkam, achieved its first criticality. This is the bridge of the program. These reactors are called breeders because they produce more fissile material than they consume. They use the plutonium from Stage 1 to sustain a reaction, while surrounded by a blanket of thorium. As fast neutrons hit that blanket, they transmute the raw thorium into uranium-233. But the engineering cost is immense. To maintain high-speed neutron flow, these reactors cannot use water for cooling. They must use liquid sodium. Sodium is highly volatile, reacting violently if it touches air or moisture. This technical barrier is so high that nations like the US, France, and Japan eventually abandoned their own breeder programs. By mastering this liquid sodium cycle natively, India has become only the second country in the world, alongside Russia, to operate this technology at a commercial scale. The final destination is Stage 3, the Advanced Heavy Water Reactor. Once India has built a sufficient stockpile of uranium-233 from the Stage 2 breeders, the cycle becomes completely self-sustaining. In this stage, reactors will run primarily on India's vast thorium reserves. Because thorium cannot start a reaction on its own, the uranium-233 acts as the spark. Once live, it continuously converts the surrounding thorium into more fuel. At this point, India's energy supply stops being a question of how much uranium can we buy, and becomes how much thorium can we dig up. This is no longer just about electricity, it is about climate geopolitics. India has committed to achieving net zero emissions by 2070. Solar and wind are crucial, but they cannot provide the uninterrupted baseload power required by a heavily industrialized superpower. Recognizing this, the government has set an aggressive target, reaching 100 gigawatts of nuclear capacity by 2047, incorporating both these advanced reactors and new small modular reactors, SMRs. India's three-stage program is a masterclass in long-term geoeconomic planning. It proves that energy security isn't just about having natural resources, it's about having the sovereign technology to harness them on your own terms. Through decades of isolation, embargoes, and immense engineering challenges, India engineered a closed fuel cycle that reduces radioactive waste, paves the way for net zero emissions, and guarantees that its economic growth can never be held hostage by international supply chains. It is the ultimate realization of atomic self-reliance.